Een van de dingen die ik in de 60er jaren al ontdekt heb, is dat wiskundige elegance, mathematical elegance, dat niet een esthetische kwestie is, een kwestie van smaak of mode of wat dan ook, maar dat je het vertalen kunt in een technisch begrip. Want in bijvoorbeeld de Concise Oxford Dictionary, daar vind je als een van de betekenissen van elegant, ingeniously simple and effective. In de programmeerpraktijk is het te hanteren doordat als je een echt elegant programma maakt, het ten eerste korter is dan zijn meeste alternatieven. Ten tweede uit duidelijk gescheiden onderdelen bestaat, waarvan je het ene onderdeel door een alternatieve implementatie kunt vervangen, zonder dat de rest van het programma beïnvloedt. En verder, merkwaardigerwijze, zijn de elegante programma's ook heel vaak de efficiëntste.
Just as I was preparing this presentation, the organizer of this Zoom session, Peter Foff, posted a post comparing C with Foff, which I think is a nice introduction to what I'm going to present today. As you may agree, the majority of Foff programmers are what we may call hard Foff or low-level hardware coders. However, in this presentation, I shall demonstrate the metaprogramming techniques derived from Foff can be applicable to many high-level programming languages and frameworks. We use the term soft Foff to refer to Foff implementation on top of high-level or the third-generation programming languages. The idea of soft Foff is not new, starting from early implementation on top of C, then Java, as well as JavaScript, Rust, Haskell, Golang, and even Lisp. However, our implementation called FoffScript, spelled PHOSCRIPT, taken from the Greek word meaning light, aims at integrating with the function libraries of the host programming language, instead of implementing the full vocabulary of Foff. As you can see on the bottom of the screen, they are the PHP FoffScript library on the left and JavaScript FoffScript library on the right. They essentially consist of these steps. Firstly, splitting a space-delimited string into tokens or words in Foff terminology. Secondly, pushing non-function word or token onto the stack, or executing the function in the host programming language by calling call user func in PHP at line 1272 on the screen, or eval in JavaScript in line 595. Note that we have introduced a colon suffix for function words that are mapped directly to the host programming language. Due to time constraint, we shall not delve into colon definition words or aliases, branches, conditions, and other more complex code structure. The code samples are available on our GitHub account, which is given together with the notes of this presentation. So the first demo program for FoffScript is an AJAX script, which sends a simple addition script from the browser front end to the PHP backend, where the PHP backend calculates the sum and returns the result to the front end. Eventually, the same concept has been extended to cover React, Redux, and even HTML, which I suspect no one has attempted to convert into reverse Polish notation. Here is a simple demo on how FoffScript reverse Polish notation generates HTML code. At the bottom of the screen is a Linux terminal where the force script commands are entered as PHP command line arguments. The script simply produces a one-cell table comprising the word Jack. The HTML output is shown at the bottom of the screen. Tree.js is a popular 3D animation library for WebGL. We have modified the original demo to include an additional tank body following the original, as well as an additional target. We then created two function words, tank colon and target colon. A JavaScript statement, m equals to new force, open bracket, closing bracket, creates an object m so that we can access the internal functions of force. The function word tank colon is used to create one additional tank body following the existing chain of bodies. Jitsi Meet is a video conferencing app like Zoom but fully open source. Its source code from GitHub can produce a web app, Android app as well as iOS app. The red text CVST colon cube underscore CVST colon and so on in the browser console on the left of the screen are force script words which maps to WebGL canvas and Tree.js functions. What you are seeing here on the right hand side where the cursor is that at the back here is actually a darkened video stream, alright, where it has been processed using the TensorFlow body mix algorithm. As you can see, there is a human figure here, and it is trying to detect the human figure and showing the result with a white silhouette, and it darkens the background. And then it has also a chat box area where we can actually use the message box here to enter force script command, and we can actually output the force script output here within the chat box. So as you can see, it's actually fairly sophisticated. After seeing what force script can do with JavaScript and other mobile and web frameworks, we shall briefly discuss Firefox 4X, a project to put forth into the Firefox browser. As you may know, WebAssembly is a major project in browser technology, which in my not so humble opinion is simply Lisp in your browser. In 2018, I attempted to put Jones forth into Firefox, hence Firefox. Eventually, I decided I should put my energy into educating younger programmers concerning using forth in high-level programming first. Then I shall let them decide if they want to pursue Firefox, which I believe may bridge the soft forth and the hard forth worlds. SimEngine, in our opinion, is a modern attempt on computer algebra that began with SimPy, a project based on Python, which marked a departure from the traditional Lisp-based computer algebra systems. We have forked SimEngine and named it as SimForth. As shown at line 313 in the video, C++ allows us to define a stack of reference-counted pointers, or RCP, a generic data structure that is used to represent algebraic terms. Here, we have an example of expanding x plus 5 to the power of 5, entered through the command line in reverse Polish notation at the bottom of the screen, which yields 5xy power 4 plus 10x squared y cubed and so on, as shown above the reverse Polish notation at the bottom. Our next example is a fork of an underappreciated project called BTOSG by GitHub user Miguel et al. That combines the bullet physics simulation engine with OpenSceneGraph. There have not been many attempts at combining physics simulation and scene graph at C++ level. Perhaps it is more convenient done at a higher level, such as Python. As demonstrated by PyBullet, a Python project utilizing the Bullet library. In the original code car.cpp, there is only one car falling from the sky. We have added a forward new car colon with some other dummy code to produce an additional 4 cars in the demonstration. The code in the video shows that we use C++ template at the bottom of the screen and function mapping at line 234 to map the forward new car colon to a C++ function sm_new car. Viewers with sharp eyes and mind might have noticed a little note that said inverse of Dijkstra shunting yard algorithm earlier in the presentation, which we did not elaborate as its significance is only apparent after we have shown examples in various programming languages. As listed on the screen, quite a comprehensive range of languages in our opinion, developed based on the very shunting yard algorithm that Dijkstra himself pioneered. The existence and applications of the shunting yard algorithm and its inverse led us to formalize homoiconism, a body of algorithms and models based on the unique feature of fourth and perhaps a selected few other languages, where data and code can be represented in a uniform syntax. As such, I was wondering, did Dijkstra know of fourth developments, and would he conquer the path I have taken to confront the problems he highlighted at the beginning of this presentation? Having demonstrated that code written in any programming language can be homoiconified or transformed into a for-script function word, it is of course tempting to consider keeping all these homoiconic functions in a graph database and to serve as a model for artificial intelligence. We wish to propose one last novel idea, that is, by traversing upwards from a node in a tree, we may then extract the key or edge connected to the node concerned. Further, such key or edge is essentially a representation of the relationship of the child node and its parent. The key, edge, or relationship may then be used to trigger one or more homoiconic functions. A homoiconic function may then produce the results as one or more nodes in the graph database. Then the cycle of upward traversal repeats itself. If a discussion on human-level artificial intelligence sounds too far-fetched, then Geisha in its reduced form at degree 0 or G0 may have a very practical application. Geisha 0 is practically a universal software management system, covering all conceivable programming languages, managed using a graph database, combining the features of Forth and other modern software engineering tools. In our next presentation, we shall demonstrate how Geisha 0 can be used to manage and extend JIT-CMIT, together with other image processing libraries such as TensorFlow and OpenCV, with examples in for-script code that can look as simple and elegant as the legendary Logo programming language.